Okay, let's begin. So last exercise, 3G, optimization. And what we'll just talk about is what is optimization first. So that's what the text at the top says. It's the process of finding the most efficient, the most effective formula. And I think you could probably reduce all engineering. Engineering is, in essence, just optimizing, finding optimal solutions, the most efficient way, the most economic way of solving a problem. Okay, so we've got a bit of a process here. I think what we'll do is we'll get into the examples and then the process will become unveiled through the examples. So we have question one. We have a TV manufacturer makes X TVs per day. The profit is given by this quadratic equation. So the profit that they're going to make is minus 0.022x squared plus 11x, take 720. That's the profit equation. Using calculus methods, find the number of TVs that provide the maximum profit and what the maximum profit is. So straight away, if we were to solve this using methods we already know, we'd probably just graph it over an appropriate V window and G solve the max. This is a quadratic equation. It has a negative A value, which means it's going to open downwards. So I don't know where its roots are and so forth, but it's going to look something like this. Okay, it's opening downwards. And we have some maximum number of TVs, some number of TVs that generates the maximum profit. And this is even true speaking in terms of engineering, because you might just think, just make more TVs. The more TVs you make, the more profit you'll make. That might be the case, but there's restrictions, such as if you employ people for more than 8 hours, you have to pay them overtime. If you run a machine for too long, it starts to wear out, so you need to do the maintenance and so forth. So there is some optimal number of TVs that generates the most profit. And that's what we're solving according to this equation. Now we know from calculus, if we're going to use calculus techniques, that turning points, so that's local maximums and local minimums, they occur when the derivative function is equal to 0. So we're going to find the derivative function, make it equal to 0, and draw its sign diagram. So the solution that we'll have here minus 11 divided by minus 0.044. Just do that quickly in my head. He's not using his head. 250. Okay, so that's the optimal solution. And in fact, we can anticipate the sign diagram. It's going to look like this. Generally in optimization they do, because we don't consider negative values. You can't make a negative amount of TVs. All right, so we have our line at 0. And we could make 250 TVs as the optimal solution. We know it's a maximum, so we have increasing to decreasing. So the optimal solution occurs at 250 TVs. Now, it's not enough to just find the X value. We need to demonstrate that it's a local maximum by drawing the sign diagram of P dash of X. And then we need to articulate our answer. Now, I believe it says find the number of TVs and the maximum profit. So that means we want the Y value when X is 250. So we can answer that in a sentence. You know, the optimal solution is the optimal amount of TVs is 250. Of TVs is 250. And profit obtained is P of 250. And did you evaluate it? 505? 905, excellent. And is it in thousands of dollars or just in dollars? Doesn't give us a unit, so dollars. Okay, so that's a pretty basic one. That's how I'll start off. Just revealing a little bit of the process there. So we're going to differentiate the function, draw a sign diagram. That gives us the optimal solution. 655. 655, close.
It was the answer in front of my calculation.
Ah, right. Okay, so let's move on to question 2. Thank you, Luke. We have a farmer wants to build a duck enclosure. He lives at Glencoe. He's getting some ducks. And we've got X and 200 take 2X. 200 take take away 2x. And this is his already existing shed. So we only need fences around this part here. And this is x. He has 200 meters of fencing. All right? So because we've got 200 meters of fencing, we have x plus 200 take 2x plus x. That gives us 200 meters. Okay, find the dimensions that provide the maximum area. So some questions are going to be tricky because they involve you developing the equation. If we look at our process on the previous page, the first thing says develop the equation. All right, we're not given an equation here, so we need to find it. Now, what do we want? The most economic solution. We want them to have the largest area, the maximum area for the ducts. So we want to know what's the area function of this rectangle. The area with regards to x is just the length times the width. So it's going to be x multiplied by 200 take 2x. That's the area of the duct enclosure. All right, and we can expand this. This is 200x, take away 2x squared. And again, that's the equation of a quadratic. Let's find the optimal solution by differentiating, setting the derivative to 0, and drawing a sign diagram. All right, so the optimal solution occurs when x is 50, right? Now read the question. We've always got to answer the question. Find the dimensions that provide the maximum area. Well, we know x is 50, and so then this length here is going to be 200, take away 2 times 50. This length is going to be 100, so the dimensions are 50 by 100 meters. Got lots of there, big enclosure for the ducks. Okay, any questions so far? All right, so now we're on to one where we have to develop an equation. Now, in a test and exam situation, let's have a read of the question and then I'll speak more about it. In an attempt to be more environmentally friendly, Coca-Cola have decided to try and minimize, we're finding a minimal solution, minimize the amount of aluminium used to make a can. The new can must still have the same volume of 375 milliliters. If R is the radius of the can, show that the height is given by H equals 375 on pi r squared. So we have a show that. Now, with these, all right, might be worth 1 mark, might be worth 2 marks. It can be a little bit tricky to access these marks, but even if you can't get it, you still have the formula for the later parts. Now, in the test situation as well, we will give you a number of formulas if you need them. So in this circumstance, we have the volume of a cylinder. Okay, you're not expected to remember it. You're not necessarily expected to write it on your cheat sheet. Something we will provide for you. The volume of the formula of the cylinder is pi r squared h. Now, we're going to use that formula. We have the volume must be 375 milliliters, which is the same as a cubic centimetre, by the way, equals pi r squared h. We're going to divide both sides by pi r squared. And we have h is 375 on top of pi r squared. All right, so we get 1 mark there for basically writing the volume is 375 and demonstrating the algebra that leads us to this equation for h. Okay, hence show that the total amount of aluminium is given by A of R, area with regards to the radius. So if you think I've got this big can of Coke here, and we've got, if we're thinking of surface area of aluminium, right? We've got 2 circles, one at the top, one at the bottom. So the area of a circle is pi r squared, and we have 2 circles, okay? So that accounts for those. And then we have this area around the outside. And the way we can think about the surface area of a cylinder is if I chop, 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 it's a rectangle. Okay, it's a rectangle, and well, that's just its height. All right, so that's just h. But what about, what's the width of the rectangle? It's the circumference of the circle. Good. So the circumference of a circle is 2 times pi times r. So that's going to account for the top, and then we have it multiplied by the height. So we have the top and the bottom, and then the outside of the cylinder. This is the surface area formula for a cylinder. Again, we would provide this to you, okay? So the surface area of a cylinder, 2 pi r squared plus 2 pi rh. Now we are asked to show that the total area used is this equation here, A of r. Now what the problem with this formula, right, is that we have 2 variables. We have r and we have h. All right, so we can't just use that formula because there's 2 variables. However, you never do anything in vain. We were asked to do this in part 1. We have a substitution we can now perform for h. We're going to put that where the h is. Okay, so we will have 2 pi r squared plus 2 pi r multiplied by 375 on pi r squared. Okay, this term out front is just going to stay as is. I've written SA, but it is area in terms of the radius because we've reduced the formula to be specifically in terms of the radius given a volume of 375, right? So 2 pi r squared stays as is. And then here we've got pi at the top, pi at the bottom, that'll cancel. We have 1 r at the top and 2 at the bottom, that will cancel. And then 2 times 375 is 750 on top of r. Splendid. Hence show, done. Okay, so part A and B, often those are the 2 trickiest parts to access, right? They're quite tricky to access, but even if you can't get them, you can still answer the later parts. You'll have an opportunity to develop the skill today. What's some advice we can give you around developing the equations? It just involves a bit of substitution. Formulas will be given to you and you just got to perform some substitution and some simple algebra. All right, let's flip the page. Using calculus methods, find the radius, the height, and the surface area that correspond with the minimum area. So this here is the area with regards to the radius function. We could graph it and g-solve the minimum, but we're asked to use the calculus techniques. So there's always a way to check your answer, right? Just from the graph. So if we know that the optimal solution, firstly I'm going to write A of r in a manner ready for us to differentiate. 2 pi r squared plus 750 r to the negative 1. Okay, we'll take the r to the top, and now we can differentiate it in one step. We're differentiating with regards to r. We have 4 pi r 750 r to the minus 2. Oh gosh. All right, so that's our derivative function. Now, in order to find the optimal solution, let's find the exact optimal solution and then we'll round it. So the exact optimal solution occurs when the derivative function is equal to 0. Okay, now whenever we have to solve an equation like this, what we want to do is get rid of the denominator. And so the best way to get rid of any denominators is just multiply both sides by it. So we're going to times both sides by r squared. On the left-hand side, it distributes, so we'll have 4 pi r to the power of 3. This term would have r squared at the top and r squared at the bottom, so they'll cancel. It will just be take 750. Remember, we wanted to get rid of the denominator. We've succeeded. And then equals 0. All right, we're just solving through for r. So we'll plus 750 to both sides. Divide both sides by 4 pi. Remember, 4 pi is just a number. It's 4 times 3.14159. And then you can think of it as cube rooting, but I reckon a better way to think of it is you're raising, remember, you have an equation. You can do anything as long as you do it to both sides. we're going to raise both sides to the power of a third. And then, following index laws, we have, if we apply those index laws there, we have 3 times a third, which becomes 3 on top of 3, which is r to the power of 1. We've solved r by itself. We have r is 750 on top of 4 pi to the power of a third. Now that's what we call the exact solution, all right? And if we were to graph this function and g solve the minimum, it's going to calculate that to a few figures. Let's evaluate that. So we'll have 750 on top of 4 pi, and then I'm raising that to the power of 1 on 3. I've got 3.907, so this is a good opportunity for me to talk about significant figures. Look at this, 907. Okay, 4 figures. We round the 4th figure, 7 rounds up, 3.91. Now, the unit is centimetres. Now, that's not explicitly clear to us. I think one assumption I'm sort of making is volume is in millilitres, and 1 milliliter equals 1 centimetre cubed. Okay, so if we've gone from a volume of centimetre cubed, it means the radius and the height are all in centimetres as well. All right, 3.91 centimetres. So that's the radius, okay? Look at the question. Using calculus methods, find the radius, height, and surface area. Now, I've said in order to prove that this is the optimal solution, we must draw the sign diagram. And you can always reverse engineer it. You don't have to graph it. We're told find the minimum. So we know it's a minimum. There's no other optimal solutions. There's only one solution. All right? And it occurs at 3.91. If there's other solutions, then you will probably need to draw it on your graph to determine its shape and so forth. But we know it's a minimum, so it goes negative to positive. Okay? Decreasing then increasing. That's our optimal solution. Now we've got R, we need H and surface area. So in order to find the surface area, we're going to put that R value into the area function. We're going to find A of 3.91. And in order to find the height, well, that was one of the very first equations that we had. Height is 375 on pi r squared. So we're just going to evaluate both of those. So that's just a calculator job. So this is 7.807, which is 7.81 centimeters. Here I've got 287.87. So 4 figures, round the 4th figure, we get 288 centimetres squared for area. So as far as our solutions go, we have 288 is the surface area, 7.81 is the height of the Coca-Cola can, and 3.91 is the radius, all with the unit of centimetres. Very good. So those are the calculus techniques that we're going to use here. So this exercise will get tricky straight away. I've listed a few formulas there that pop up in this exercise specifically with the tricky ones. Again, if you need a formula, we will provide it for you. So any questions about what we're going through so far? Excellent.